Hi there, everybody, and welcome. This is Professor Thayer with you here this evening to talk to you about physical chemistry for the life sciences. And today we are going to have our first macroscopic lecture, which is about the ideal gases. So let's get started. Turn this off. Share the screen. Oops, let's see. Share the screen. Share the screen. Share screen. All right, and here is our lecture. All right. So up to this point, we have talked about quantum mechanics. In quantum mechanics, we have been dealing with the subatomic particles. And subatomic particles are great, but what about the rest of the world? We live most of our time in the macroscopic world, and so many of the things that we're going to need to talk about in this part of the class are going to involve working with molecules, ensembles of molecules, larger things than that. So up to this point, we saw like particle in a box, one-dimensional harmonic oscillator, rigid rotor, and how we could calculate electrons going around hydrogen, helium plus, or regular helium. And already these require a number of approximations. So now we want to scale it up and we want to talk about the bigger picture, macroscopic view. That's one of the important things about thermodynamics, for example, that we'll get into not today, but coming up. And that has to do with how do we bridge the microscopic world of individual particles, which already is macroscopic compared to the what we talked about so far in the quantum mechanics world. But thermodynamics is about individual molecules and then scaling up to ensembles of molecules. So this will be our bridge between the microscopic and the macroscopic worlds. So you've probably already heard of the ideal gas equation, PV equals nRT. So that's pretty much where we are going to begin. So ideal gas. So there are some properties of the ideal gases. Ideal gas properties. They are point masses, which means they have no size or shape. This is obviously a theoretical construct because there's not really such thing of as a point mass. But again, we're talking about ideal gas, which of course itself is a theoretical concept. But many things do approach the ideal gas. We'll find out that a lot of things in physical chemistry are treated as ideal entities, and then we scale up from those by looking to see what would happen as things become non-ideal. The particles are non-interacting. And also we have this idea that all gases behave ideally. When they are sufficiently dilute. And so this then suggests the idea of ideal conditions. That is, ones that promote ideal gases. So if we want the gases to be dilute, what would we want? This means we want a high temperature, because otherwise the particles wouldn't be moving around, right? If they were cold, they would be contracting and all really close to each other, and then they'd be interacting, and that's not the ideal condition. So hot is what we want. And the other thing we want is we want the low pressure. And this is because if the pressure is high, it's going to push the particles together. So how do you get it to be so that the particles aren't close together in terms of pressure? Well, you have the pressure be low so that the particles aren't close together. So in other words, non-ideality happens when these things fail. Non-ideality arises when the ideal gas properties fail to hold. In other words, it's the opposite of the ideal condition. So if you want non-ideality, you want low temperature and high pressure to push the particles together, and that's when you'll get your non-ideality. All right, so let's write out the ideal gas equation. We're actually going to write out two versions of it. We'll have the regular ideal gas equation, and we'll have the molecular ideal gas equation. No, sorry, that's not the right word. It's molar. Molar. Oops. Like, why is that like that? So the regular ideal gas equation you've probably heard. PV equals nRT, and the molar ideal gas equation is PV bar equals RT. Well, they must be the same thing, right? So how does this work? All right, so P is for pressure, V is for volume, N is the number of moles of particles, R is the ideal gas constant, and T is the temperature in Kelvin. All right, so great. What about this one over here? Well, all the variables are the same except for this V. What is this V bar? V bar equals the volume per mole equals V over N. So this is why the formulas are nearly identical. Notice that if we simply just took the N on the left version of the equation, the ideal gas equation, and moved it to the other side of the equation and divided volume by N, we'd have volume per molecule, basically, right? Because mole is really telling you how much stuff do you have. So you'd have the volume per molecule, which is what V bar is. So V bar really equals V over N. This is actually a really interesting transformation that happened. I mean, it might just seem like some algebra, and I mean, like, why not just divide P by N or divide something else by N, right? And it seems like maybe not a particular reason to do that, but let's explore that a little bit. So we have extensive versus intensive properties. So this is, in other words, V versus V bar. So an extensive property means that it's directly proportional to the size of the system. This thing that looks like an alpha is the proportionality symbol, directly proportional to the size of the system. For example, volume. Obviously, the volume depends on the size of the system. Okay, now we also have an intensive. Does not depend on the size of the system. So this would be, for example, pressure, temperature, and density. So then, by converting from V to V bar, notice what we've done. We've gone from an extensive property to an intensive property. Oh, and I haven't, oh, no, okay, that's good. Gone. Too intensive. Sneaky, huh? All right. The next thing we want to look at is calculating the pressure. Pressure equals F over A. This is force per unit area. I'm going to use the height of a column of mercury to measure pressure. So you may have heard of mmHg is millimeters of mercury as a measure of pressure. And the reason why is because mercury columns actually used to be used to measure this property. So the way the setup goes is something like this. So you may not have ever experienced working with a mercury column, because of course mercury is poisonous. We have a vacuum. This is an upside down tube, by the way, and mercury is kind of a shiny color. Let's see if we have a shiny. Some mercury in here. Oh, look at that. It's even a shiny color. How nice. All right, so this is the mercury, which is in the tube. And if you flip it upside down, gravity, of course, pulls on it and will pull some of it down. And so that's how the vacuum gets made, right? This is a glass tube, no openings, except, I mean, this end is open, but what we're going to do is we're going to submerge it. So what we do is we now have like a dish like this. And there's more mercury in there. Oh, I need the pen again. Color, different color. On mercury color. So there's also mercury down in here. Like that, so that the mercury, there's like excess mercury and there's some pressure, and this tube is submerged in it. So what that means then is it can't have any coming out. And if there's pressure on the external world by the atmosphere, then it's going to push the mercury back up. So in other words, it's a balance between the mercury's tendency to fall down and create the vacuum, but the vacuum is sucking it back up, and the external pressure out here. and that will lead to the mercury being at some equilibrium level. All right, so let's see how we could figure this out. We could begin with pressure equals force per unit area. This was given. This is the definition of pressure. Now, we can substitute in pressure equals mg over A, where G is gravity, right? What's force in the gravitational field? It's gonna be G, gravity. So we're gonna sub in F equals mg. F equals ma, right? G is the gravitational version of that. All right. Now, we also have the density. Okay, so now we're gonna have P, A, oops, wrong A, equals M. Okay, so this is a given fact. Okay, this row, that's rho, it stands for density. It works because of the unit analysis. Which is really just mass over volume. H is height. A equals area. And V equals volume. Now, we can substitute this in. So notice that we have an M here and we have an M here. So we're gonna do this. Substitute this in, but we'll use the other side of the equation because they're equivalent. So in other words, what we've got now M equals A. All right, so now what does that give us? So that gives us P equals rho HA G over A. Oh, guess what? We can do some canceling. Great. Always like things to be a little simpler. So now we have P equals rho HG. Now remember, we've been using Planck's constant lately. So let's just be clear, this one is the height. It's not Planck's constant, it's normal height. So now the pressure can be calculated knowing just the density and the height and of course the gravitational constant. So let's see how we could use this example. Calculate the pressure exerted by 76.000 centimeters column of mercury. Right, Hg is mercury. Remember that. The density of mercury equals 13.59 grams per centimeter cubed. Okay, so how do we solve this thing? First, we're going to write the formula. P equals F over A equals rho Hg. Write the formula. Given. All right, what's next? Sub in your data. 13.59 grams per centimeter cubed times 76.000 centimeters times 980.67 centimeters per second squared. And now we can just simplify that. 1.013 times 10 to the 6 gram per centimeter second squared. And that's how we can calculate. All right, next topic. What is T? It's temperature. An operational definition. And the Kelvin scale. So, did you ever wonder why we need the Kelvin scale anyways? I mean, we have degrees centigrade, and we also have Fahrenheit. Why do we need another one? It's the latecomer. It seems kind of like a me too kind of a thing. So here we're going to talk about some important elements of design in the Kelvin scale that make it especially useful. Establishing the minimum temperature. So that's absolute zero. So about absolute zero, the temperature at which all thermal motion ceases. The volume is zero. So this is because we're talking about point masses. So obviously these things are theoretical also. So the Kelvin scale is built with this in mind, and the absolute zero is the 0 Kelvin mark. Let's understand why. Let's begin with the ideal gas law. Now we're going to solve T. Oh, oops, wrong side. Right, that's easy enough. Here's T. How do you isolate the variable? Well, we're just gonna move things to the other side of the equation. So T equals PV bar over R. Gases are going to behave ideally when pressure is equal to zero. So that means for an ideal gas, we take the limit as the pressure equals zero. take the limit as p approaches 0. T equals the lim of p goes to 0. Do you remember this from your calculus? Notice that all of these need to be positive numbers. Doesn't really mean anything to have a negative volume or negative pressure, and R is also positive. So in other words, all of these terms are going to be positive. E and V bar are greater than 0, and R is a positive constant. So in other words, none of these can have a negative value. All right, so what does this mean? The lowest possible value for I, lowest possible T is 0 Kelvin. Let me establish the size of 1 Kelvin. Kelvin is defined to be 1 over 273.16. This is the triple point of water. All right, so what we can do is we can linearize the equation. Let me tell you what I mean by this. Given if PV bar equals RT. Now we're going to solve for V bar. So that means we're coming in after this variable. How are we going to do that? Well, V bar equals RT over P. So we want the volume as a function of temperature. We have V bar of T. Now it is asking how the volume varies with the temperature. We can write the equation. Oops. Or over P times T plus 0. Oh, Y equals mx plus b. It's the equation of a line. This is the slope. This is the y-intercept. So what we can do is we can actually make some plots. As now we have the equation of a line. said, X is temperature in kelvins. Now, the thing about these lines is they all extrapolate to 0. This is 0.010 atmospheres. This is 0.020 atmospheres. This is 0.030 atmospheres. Oh yeah, let's just put our units over here. This is V bar and liters per mole. It's like 4. That's right. Liters per mole. And this scale goes up to something like 2,000. There's 1,000. Here's how we linearize an equation. V equals nRT. It's given solve for V. Is a function of T. Oh wait, I already used this. All right, great. I already linearized the equation. Sorry. Already did it. Oops, that. All right. Next, we want to derive the volume of an ideal gas. And here we go. We already looked at temperature in the limit as P goes to 0. Now we want to look at V bar's limit of P goes to 0 at 273.15 Kelvin. This will tell us the volume of a gas with temperature in the limiting ideal gas, ideal case of no pressure. So now we can do something like this. P V bar R T P V bar equals R. Now we said we're going to substitute in the temperature 273.15 Kelvin, the triple point. We then make a plot of PV bar. PV bar versus P. Now, I could use at varying pressures, or T equals 273. And see that as P goes to 0, V bar goes to 22.414 liters. Very precise. So let's see how this would look. This is the line for H2. Well, it's kind of a little extra long. All right. Yeah, the ideal gas. We have N2. And we have CO2. So we see that what we've done is we've made a range. Well, actually, the range came out from the graph. So these are interacting particles. And these are ideal particles. Interacting. So this side is more ideal. This is less ideal. This all extrapolates out to the volume of 22.4. You probably learned this number at Gen Chem. Liters per mole. Where did that number come from? Well, here it is. So you can say the volume of ideal gas at 22.414. You learned in Gen Chem. We can also solve for R. So we have R equals dV bar over 273.15 Kelvin. That's the temperature. And we can solve. Okay, so this is okay. So now we're going to plug in the PV bar. So now we're going to have R equals 2.414 liter atmospheres per mole. And here's the temperature. Oops. Okay, here we go. Now, so equals 0.082058 liter atmosphere per mole. So this is where we get the R from. It's also available in SI units, which could be converted to R equals 8.314 joule per mole Kelvin. So this describes then how the ideal gas behaves. So ideal gas behavior holds under some conditions for some gases, but how do we handle real gases which may not be under ideal conditions? We could develop some treatments which are introduced to, which are going to be correction factors dealing with the non-ideality. So we'd need to know was information about various particles. So gases are not actually point masses, and gas particles are actually do interact. So let's see what the evidence for non-ideality is. dV bar T given the gas equation for side. So this is just moving the items around in the equation. So, what did I do? One equals dV bar over RT for real gas. I'm measuring a deviation for dV equals RT for a real gas, then the non-ideality would be observed, right? So if this is how the ideal gas behaves, then we should be able to rearrange the equation and it should be equal to 1. But any change from ideality would deviate from the 1. And we can use this. So this will be the ideal gas equation. We can also define Z. This is the compressibility factor. So in other words, Z is just a measure of non-ideality. So this is what the graph will look like. Here's C and here's P. So for an ideal gas, Y equals X. What a real gas looks like. Yeah, we can change the color. Okay. This here is the attractive forces. Which dominate at low temperature. This is because the particles are close together. Here is the regime above that. This is repulsive forces. This side means repulsive forces dominate, which spreads them apart. So the ideal gas is closer to the top. So we know that that's the case, then maybe we need to have some plan for how to correct these things. This is the Van der Waals equation. All right, so you can do it like this. E plus A over V bar squared V bar minus B equals RT. A and B so A and B are the Van der Waals constants. Particular to a gas. They correct for the assumptions. They will correct for the interaction of particles. So A is equal to 2 pi times n sub a squared c sub 6 over 3 sigma squared. Right, so some of these things should be mentioned. So this is the radius. This is the Leonard Jones term. There'll be more on this shortly, so you should stay tuned. All right, great. So then, what about P? Oops. No. Yeah, B corrects for volume. So we're just doing point masses. That's why we need this. E is equal to 2 pi sigma cubed over 3 and sub A. So these are all table lookup values. Yeah, I remember this is up there. So they're equations of the cubic form, v cubed, and so they're generally more accurate than van der Waals. We're just getting increasingly sophisticated in how we're going to correct for the errors by using more and more complex modules. So in addition to this, we also have more equations. So we have other equations. But they're all basically achieving the same thing. So there's the Riemann equation. It looks like this. RT E A B bar times B plus beta. Wait, E equals RT over B bar minus beta minus A. Yeah, this is not that clear. I added more in minus A over T to the 1/2. That means the square root, right? B bar times B plus beta, and this is not that clear. That's better. So you would look up parameters. And we also have another one. We have the Pang-Robinson equation. So you see that it's just really the same thing. It's really P equals nRT repackaged in many forms with some corrections. Let's put the parentheses around the other term. Minus alpha over V bar times V bar plus beta plus beta times V bar. That does not look like beta. Beta and V bar minus V beta. Alpha is a temperature dependent parameter. Beta is a table of quantity. This can be expanded out to equation. This could be expanded out. But I don't think we're gonna really take the 857. All right, so example. Use the Lick form equation. We calculate molar volume of a thing at 300 Kelvin to 200 atm. So we'd do something like this. It expands out. Raising something to the 1/2 power is the same as taking the square root. You'd then just substitute in the values. These are all table lookup values. So it would look like something like this. All right, so you're just plugging all the values into the equation. So it's good practice to keep track of your units. This can help you relieve a lot of problems. Okay, we'll just keep going. Just go to bar. Oops. And the next term. Ew, that's a really long one. I'm going to like that. Cubic. So, yeah, I'm not gonna show every single step of the algebra here. You get e bar cubed minus 0.1231 e bar squared plus e bar minus 0.0271 equals 0. It's a cubic. Recognize because of this leading term up here is to the third power. So you can solve by graphing. Use a graphing calculator. We look for zeros. Alternately, it could be solved by a method called the Newton-Raphson. You may have learned this in your algebra class, but I think the simplest thing to do is just solve it on your graphing calculator. We also have something called the law of the corresponding states. All right, the next thing we're going to talk about is the corresponding states. Law of corresponding states. This is actually a pretty cool thing. It says that the properties of all gases are going to be the same if they're compared under the same conditions relative to their critical point. Now, keep in mind the critical point is the point at which solid, liquid, and gas are all interchanging with each other. And so the critical point, of course, is going to be dependent highly on the mass of the thing that you have and the amount of interaction that it has. So the law of corresponding states sort of is like normalizing for those properties and saying that the way a gas is going to behave is going to be, well, relative to that triple point. So let's write that down. Properties of all gases are the same if they are compared. Under the same conditions relative to their critical point. It's also known as the triple point. So for example, we have the van der Waals reduced equation. And I'll show you how to calculate these in a second. So notice we sort of have like a P, V, and T, right? There's almost the PV equals nRT all over again. PR plus 3 over V bar R squared times the R, VR minus 1/3 equals 8/3 T sub R. This is sort of like V bar equals sort of kind of, because the R now, so we have all these reduced quantities, so the R is now gonna be changed out. So notice that this is just a variation of PV equals nRT, because V bar we know is really just V divided by N. And so now we have this variation. We're going to have 8/3 here because the R is going to be modified because we're using the sub R values for all of these things. So the R subscript means it's the reduced value. The C subscripts, which aren't on the screen yet, means it's at the critical point. At the critical this is how to calculate those values. So P sub R, this is the given pressure over the pressure at the critical point. V bar sub R equals V bar, the given molar volume over the one at the critical point, and TR, temperature, given over temperature at the critical point. So this says that all gases behave the same under their corresponding states relative to their respective critical points. So what you might want to know then how to do is how do we calculate this stuff? Compute the corresponding states. Of CO2 in the gaseous states and N2 also in the gaseous state for volume PR, our molar volume equals 20 and temperature TR equals 125. How come these things don't have any units on it? That's not right, is it? Well, it's because these are the reduced forms and they have the units on them up here, but notice that they're gonna be a pressure over another pressure, for example, and the units are gonna cancel out. So the sub Rs don't actually have any units on them. Think of PV equals nRT and you know V and T, we're gonna calculate P because it's not the known thing. Instead of PV equals nRT, we're gonna use the corrected formula. As we pointed out, it's pretty close. So this is how you solve it. VR plus 3 over VR, V bar R squared times V bar sub R minus 1/3 equals 8/3 PR, right? This is given. And what do we do next? Sub in the data. All right, so you obviously need to have a data table with these are available information. So PR plus 3 over 20 squared 20 minus 1/3. So we're trying to solve for P here equals 8/3. And then the TR is given at 1.5. So we substitute in the data. Yes, we have this information from the question, right? This is the 1.5. This went to there, and this other one here, it's 20, went to this. It went to a couple of places. This 20 and this right here. And so that's how we can do this. All right. One would obviously need to know those numbers then. BR equals 0.1958. Right. So some algebra. Algebra and calculus happened. And we solve for that. So you'd need to multiply this out, and then you would solve for the piece of art. And you would, so you multiply it out, move the concepts over to this side, and obviously you're going to just multiply all those together. But I think you can handle that from here. So this means that we now have the reduced info. P sub R equals 0.196. P sub R is 20.0. And T sub R is 1.5. So next we can figure out the corresponding PPT for the particular gas. To recall that we are looking for the corresponding states of gases, which are going to be different due to taking into account the non-idealities of the particles to each of them. So this is how we can do this. I'm going to need to make a little table. We'll have the formula. We'll have the calculation for carbon dioxide, and we'll have the calculation for nitrogen gas. P R equals P over P C. So we'd look up the values. 0.196 equals P of CO2 over Yeah, so you need to look up the critical point from a data table. 72.877 atmospheres. So the P plus CO2 equals 14.3 atmospheres. And we do the same thing over here. These are table values. So P of N2 equals 6.58 atmospheres. We do similar. Okay, so the idea here is P sub R is the same for all gases, V sub R is the same for all gases, and T sub R is the same for all gases. Why is that? Because of the law we were just talking about, the law of corresponding states, which says that it's going to be the same for all gases. All right, so now we're going to solve the same thing for V sub R equals V bar over V sub C, V bar sub C. And so, yeah, this could be organized a little bit better. All right. Right, now we're gonna need to calculate for carbon dioxide. Okay, and also this. All right, good. So now we need to calculate the values here. V bar CO2 over 3.9. All right, so we're just subbing in equals N2 over the lookup value of 0.09 liter whole bar N2 equals 1.802 liter per mole. It says liter per mole. All right, that's that calculation, and let's continue our table here. For our next box, we're going to have P sub R equals T over P sub C. So what's the value? 1.5 equals T over CO2 over 304.14 Kelvin. That's T sub CO2 equals 456.21 Kelvin. And we can do the same thing over here. Whoa, that was weird. T sub N2 over 126.20 Kelvin. T sub N2 equals 189.3 Kelvin. All right. This one. All right. So, and in other words, at these PVTs values, the gases CO2 and N2 will behave the same. These are their corresponding conditions. Conditions. All right, so today we have talked about the ideal and real gases. So probably already know about PV equals nRT before we met today, and maybe even knew about the ideal gas conditions and properties. So ideal gases are the point mass and non-interacting particles. But of course, most gases are not actually like that. They're real. And so some of the things we want to understand is how do ideal gases behave and how do we understand real gases with relation to the ideal ones. And this is something that's going to underlie a lot of PCAM, and that is that we're not actually going to be able to solve a lot of the problems. So we're going to just make up ideal situations and then we're going to compare, and that's how we're going to proceed. So we saw that ideal gases have their behavior under high temperature and low pressure. And basically, whenever something deviates from that, that's when the ideality starts to show up. So we look at the ideal gas equation, and we also took a look at the molar idealized gas equation, and that brought up the idea of extensive versus intensive properties. And we also saw how we can measure pressure using the columns of mercury. And this also we are able to take a look at how we get some of the values that we do. So this also brings about a theme we see in PCAM, and that is that we're going to need to derive equations from some of the basic ones to like linearize things, for example, so that we can understand where things come from. And so this is what we worked through here on linearizing the equation here, so that we linearize the equation to see that this all has an intercept of 0. And we also were able to look at getting the volume that we all learned in Gen Chem about the volume of a gas, also by linearizing an equation and solving. We also were able to solve here for the constant R, which is given in the liter atmosphere per mole Kelvin, although you may see it more often in other units, but you can interconvert the units, that's easy. So then we were able to use this information to look for evidence of non-ideality, which meant when gases are not behaving in their ideal equation. And so this compressibility factor basically was able to show us the same thing, because under ideal conditions, we would have this compressibility Z versus pressure would just be like y equals x. So it would be a line that would go on the diagonal. But we saw that it, in fact, actually real gases have lines that don't go along the diagonal. And we see that it has basically two regimes, the attractive and the repulsive regimes. And so then this brings up the idea of, well, how do we actually go about correcting for non-ideality? And we saw the van der Waals equation as the first example of that. So you can substitute in these various correction factors, but it's basically PV equals nRT, but N just gets wrapped into V, and we have the correction factors of the A and the B that we would substitute in order to get those values. And that's a pretty simplistic way, but we can understand how that might work, because we could see that it's just a correction on those terms. But we could do this in an increasingly difficult way. So the Riedlich-Kwong equation and the Ping-Robinson equation are some of the examples of equations that are out there that do this. And then we saw a calculation with this, with the Riedlich-Kwong equation, but essentially you just substitute things in and solve. There's nothing too special going on here. And finally, we took a look at the law of corresponding states, which states that all gases are the same if they are compared under the same conditions. So again, we see that this is very much related to the PV equals nRT equation. And we saw how to calculate these reduced values, which essentially is the value that's given divided by the one at its critical point or its triple point. And so when we do this, we see that they have similar behaviors. So we were actually able to work this out for the example of comparing two common gases. So we looked at carbon dioxide and N2. So we needed to compute the reduced values for them, and then we used our reduced, we made a little table with the reduced values, and we calculated this out for these two gases to get the values of PB and T that are going to be the ones at which the gases are going to behave the same. All right, well, I bet you never knew there was quite so much to the ideal gas equation, but it does give us insight into quite a lot of things. And as we saw, it has the ability to help us understand some of those constants that we have learned in Gen Chem for the gases. So thanks so much for joining us, and we will continue our discussion of physical chemistry next time. See you later.